Hello, everyone. Today we are going to talk about unbalanced forces, which really just comes down to Newton's second law. So what is Newton's second law? Newton's second law is the idea that the sum of forces acting on an object is going to be equal to the mass times the acceleration. Or you might hear this as F equals ma. Now, I'm going to be very specific about my language by saying net force equals mass times acceleration, and we'll go into that why in a second. So if I look at this equation, as force increases, the acceleration also would increase. So if I push something with more force, it's going to have more acceleration. This is a constant, this is a direct relationship, or you could say proportional. And this is when mass is constant. So if the mass of the object isn't changing. Now we can look at this a little differently. If mass were to increase, thinking about my equation, if mass increases, the acceleration would have to decrease. This is an inverse relationship, and this is when force is constant. So if I keep pushing, like imagine I'm pushing a shopping cart and someone keeps adding stuff and adding stuff and adding stuff, and I keep pushing with the same net force, that acceleration, that cart would have to slow down. Now, you're going to see this equation on the AP equation sheet looking like this right here. Acceleration equals F net over M. It's just rearranged to equal sum of forces equals MA. I want to show you where this is at on the equation sheet. So looking at your equation sheet, it's going to be right here. You'll see that it says sum of forces, the sigma F over M, and net force over M. They mean the exact same thing. So let's actually look at some problem solving techniques when it comes to this. Things we're going to do every single time. And I still do this even to this day. You're going to establish a system. Really realize, what does your dot represent? Then you're going to draw a free body diagram or a force diagram. You're going to determine which direction is your positive direction. You're going to solve for each individual force that you're capable of solving for without summing the forces. Then you're going to find your net force. Every force that acts in the same direction adds. Every force that acts in a different direction subtracts. And then you're going to solve for whatever the problem's asking you for. So we're going to do this. If I lift a 30-kilogram object with a force of 400 newtons, what's the upward acceleration? First thing we're going to do is draw a force diagram. So force gravity acts on every object that has mass, so you automatically start there. And we have an upward applied force. We're told that this applied force is 400 newtons. And we have the ability to solve for force gravity by saying m times g. So 30 times 9.8. This gives me 294 newtons. So we have established our system. We've drawn our free body diagram. I forgot to say we're going to make up positive. Most of the time, up's positive, down's going to be negative. There are some circumstances where that's not the case, though. We're going to find individual forces. Did that. Now we have to find the net force. So we're going to say the sum of forces is equal to MA. I just start with Newton's second law right away every single time. And I'm going to say every force that's going up is positive. So applied minus gravitation. So did that. Check. Now we're going to plug in everything we need to know and solve. So 30 is my mass. We're solving for acceleration. Equals 400 minus 294. Now it's just an algebra problem. The physics is actually over. 400 minus 294. This gives me 106. And divide by 30. This gives me an acceleration of 3.5 meters per second squared. So this is the correct way to do this problem. I want to show you a mistake a lot of people make so you don't make it. A lot of people, if they have the idea that force is equal to mass times acceleration, they're going to see this problem right away and go, okay, I've got a force. That's 400. I've got a mass of 30, and we need acceleration. 400 divided by 30, they're going to get an acceleration of 13.3 meters per second squared. This is not correct because we have to take the sum of our forces. We cannot forget that the gravitational force is acting on the object because that's going to make it more difficult for me to lift it, which means I have less acceleration. Do not fall for this bottom one. I can guarantee on multiple choice tests. I'm going to put that answer on there. And if you do it wrong, you're going to find your answer. Don't be that person. All right, let's look at a little more complicated of situations because, to be honest, this is about as simple as it's going to get. Let's get a little more complicated. So we've got the earth exerts approximately 100 Newton force on a 10 kilogram suitcase. Suppose you exert 120 Newton force upward on the suitcase. Same setup we just did. If the suitcase starts at rest, how fast is it traveling after being lifted for 0.5 seconds? So this is where we're going to take kinematics from last unit and combine it with forces. We're going to start the problem the same way, drawing a force diagram for my suitcase. I've got an applied force upward for me, and I've got a gravitational force downward. They give me this information. It says I've got 100 newtons of force. That's what the Earth's exerting. And it says I exert 120 newtons. We're going to sum our forces and set it up. By the way, up is positive. And say MA is equal to my applied force minus my gravitational force. So we get 10A equals 120 minus 100. 10A equals 20. So in this situation, we have an acceleration of 2 meters per second squared. But that's not where this question ends. If you ever see it ask for velocity, if it gives you a time, that is a big red flag to me that I need to also use kinematics. So for the second part of this problem, we know acceleration is 2 meters per second squared. We know my object's going to start at rest. We know we've got a time of 0.5 seconds, and we want to solve for VF. We have to go back into that toolbox that we have and pull out kinematics, and I'm going to decide, looking at my 3 kinematic equations, remember, they are VF equals VI plus AT, XF equals XI plus VIT plus 1/2 AT squared, and VF squared equals VI squared plus 2A delta X. Looking at my knowns, I can use the first kinematic equation. So I'm going to say VF equals VI plus AT. We're solving for how fast our object's going. So I'm just going to plug in what I have, which gives me a final velocity of 1 meter per second. So after I've lifted my suitcase for a half second, I get 1 meter per second of velocity. All right, one more example for you. Again, we're going to go another level deeper. Michael Holmes is 70 kilograms, was moving downward at 36 meters per second and was stopped by a 2 meter high of shrubbery on the ground. Estimate the average force exerted by the shrubbery and the ground on his body while stopping. So the shrubbery and the ground. So we've got this situation before. We've got Michael and he's falling. He's just falling like this, just force gravity. And then we've got, as he's stopping, we've got force gravity down, and we've got a applied force. You could call it a normal force of some sort. I'm still going to say up is positive. So we are given some information at the beginning. We know he's got an initial velocity of 36 meters per second. If he's stopping, we know we're going to have a final velocity of 0. My initial height is going to be 2 meters. My final height is going to be 0 meters. Now, he is not in free fall while he's stopping. So acceleration is not negative 9.8. We actually need to solve for what the acceleration is. Looking at my list of knowns, I don't have time. So I need to use my third kinematic equation. VF squared equals VI squared plus 2A delta. I'm going to put Y because we're moving in the Y direction. VF is 0. VI is, oops, that's not a plus sign. VI is 36. Plus 2, A is what we're solving for, times negative 2, because he's going down 2. So 0 squared 0, 36 squared is 1296, and then minus 4A. I'm going to move my 1296 to the other side. And then divide by negative 4, which gives me an acceleration of 324 meters per second squared. That is really high. That's okay. It's a person stopping over a short distance. I think that number checks out to me. Now we want to solve for what is the acceleration, what is the force acting on his body? Now, sum of forces equals MA. We're going back to that summing of the forces, and we've got an applied force upwards and a gravitational force downwards. Now, this whole first chunk before was literally just to solve for acceleration because, again, red flag to me when I'm given a bunch of kinematic information, I know I'm going to have to use kinematics. His mass was 70 kilograms. So we've got a mass of 70. We've got an acceleration of 324. We don't know the applied force. That's what we're looking for. Minus his force gravity, because that's not part of the applied force. So 70 times 324, this gives me 22,680. And then 70 times 9.8 gives me 686. So to solve for this applied force, I'm going to add that to the other side, add my two answers together, which gives me an applied force of 23,366 newtons. That's a lot. But that's our correct answer. So really what I want to point out, I'm still approaching these problems no matter what the same way. Draw the force diagram, identify my positive direction, sum my forces, and then solve for what I'm missing. Sometimes you're going to have to use kinematics to help you get those missing values, and that's okay. All right. I've got a couple other examples with this set because this is just the intro to it. Please make sure you watch those other videos if you're struggling with this or really struggling to wrap your head around these problems.